This question says, the rate constant of a certain reaction is known to obey the Arrhenius equation and to have an activation energy of 70 kilojoules per mole. If the rate constant of this reaction is 21 molar to the minus 1 seconds to the minus 1 at 148 degrees C, what will the rate constant be at 246 degrees C? So this is a pretty complex math problem where we need to start by deriving an equation, and then we need to use the equation that we derive in order to solve the problem. Now, if you flip to the Alex explanation, it will derive the equation for you, which you can directly use. But in my experience, sometimes seeing an equation derived helps me to remember the equation and what the equation means. So I'm going to do that for you. So essentially, we have two reactions, right, with two different rate constants. The temperature affects the rate constant, so at 148 degrees C, this is the rate constant, and we want to know what the rate constant would be at 246 degrees C. We can assume that it will be higher than this number, because the reaction will proceed more quickly at the higher temperature, but we don't know exactly what it is, so we need to use the Arrhenius equation. Actually, we need to use two of them to figure this out. So I'm going to write the first Arrhenius equation, K1 equals A, the frequency factor, which is essentially the fraction, a number between 0 and 1, of the molecules that collide in the proper orientation. E, the natural log, or actually the inverse of the natural log, to the negative EA, the activation energy, over RT, R, the gas law constant, in this case, it's 8.31 joules per mole K, times T, the temperature in Kelvin. Note that R, you may be familiar with from the gas law equation as 0.08206, and that's liter atmospheres per mole K. In this case, it's joules per mole K, so it's just a different unit. That's why it has a different value. I should also indicate that this is the rate at temperature 1. The activation energy is constant for the reaction, and R is constant for the reaction. So the next thing we need to do is write it for the second reaction. K2 equals A, EA, E to the negative EA over RT2. So that's basically what we need to do. So essentially what this is saying is that the rate of the reaction will increase as the activation energy decreases, because we are taking this to the negative exponent. So the larger that this value is, the smaller the rate of the reaction. So at higher temperatures, since this is on the bottom, the reaction will go faster. And if the activation energy is lower, the reaction will go faster because we will have a negative number here raised to an exponent. So basically now what we need to do is simplify this into one equation. And to do that, we divide. And then when we divide, we can kind of cancel out like terms and simplify. So when we divide on this side of the equation, we get K1 over K2. And believe me, that is definitely the easier side of the equation to simplify. We'll spend a few minutes simplifying the other side. Equals, A's go, because that's a constant, so therefore we can cancel it out. And then we have E to the negative EA over RT1 divided by E to the negative EA over RT2. Now I'm going to focus on simplifying this side of the equation. This side of the equation is already pretty simple. This side, not so much. So now we're dividing exponents, which is the same as subtracting. So I'm just going to focus on this side. We can rewrite this as E to the negative EA over RT1 minus E to the negative EA over RT2. So we rewrite it like this. We can further simplify this. I'm just going to shift the paper down to E to the negative EA over RT1 minus negative EA over RT2. So now E is raised to this entire power. Because we're subtracting exponents, we can bring the E out and we can subtract them and then take the exponential here. So basically, we went from this whole expression minus this whole expression to we pulled the E out, and then now we have minus EA over RT1 minus EA over RT2. Now what I want to do is pull out negative EA over R because it's in both cases. So we can rewrite this as E to the negative EA over R times 1 over T1 minus 1 over T2. And now, after all that work, we have a simplified expression. So going back up here, this equals E to the negative EA over R times 1 over T1 minus 1 over T2, and all of that is equal to K1 over K2. Now, let's plug in what we know, and I'm going to do that over here. Well, we know K1, it's given 21 point, and that's 1 over molar seconds. K2 is what I'm trying to find, equals E to the negative activation energy. Note that R is 8.31 joules per mole K, and the activation energy here is given in kilojoules per mole. So we do need to convert this to joules, or you could convert this to kilojoules, it doesn't really matter. But I'm going to convert this one to joules, and I'm going to put it in as 70,000 joules per mole divided by 8.31 joules per mole K times 1 over T1. Okay, and mind you, the exponent is raised to all of this stuff. So it's all of this in the exponent. So it doesn't look like that, but that's what it is. The temperature needs to be in Kelvin. So the T1 is 148. I'm going to add 273 to that. And I'm going to get 421 K minus, in this case, the 246. I'm going to add 273 to it. And I'm going to get 1 over 519 K. So I've now simplified this expression. This side I'm not going to do much with until the end. 21 times 1 over molar seconds divided by K2 equals E, I'm going to simplify this, 70,000 joules per mole divided by 8.31 joules per mole K. It's still going to be negative because it's negative over here. And what you get is 8424 K. And I'm going to ignore the sig figs because at the end it says please round your answer to significant figures. So I'm going to go ahead and ignore those for now, just to not induce any more confusion. So I just took 70,000 divided by 8.31. This is joules per mole. This is joules per mole K. So basically, when you do that, you get K as the unit. The joules per mole cancel out, and the K comes up to the top because it's on the bottom, if that makes any sense. Then I want to simplify this expression, 1 over 421 minus 1 over 519, and I get 0.0004851, and the unit is 1 over K because it's per K in both cases. Now I'm going to multiply these two numbers, so I get 21.1 over molar seconds divided by, I'm just going to move the paper down, K2 equals E to the negative 3.778, which I just took this number times this number, and that's what I got. I'm going to now take the inverse of the natural log of this, or the 2.3, whatever it is, and raise it to the power of negative 3.778, and I'm going to get 21.1 over molar seconds, K2 equals 0.02264. Now to simplify, I want to multiply both sides by K2. Cancels out over here. K2 goes over here. And then I want to take my 1 over molar seconds equals 0.2264 K2. And I want to divide by 0.2264. Divide by 0.2264, And what I find is that K2 equals 21 divided by 0.2264, which is 927, and it has the same units, 1 over ms, which on Alex, as you probably know, is molar to the minus 1, s to the minus 1. It's the same thing. And I need this as 2 sig figs, which means scientific notation. Since I can't really write it as 930, I'm just going to convert it to scientific notation, which is equal to 9.3 times 10 to the 2 molar to the minus 1 seconds to the minus 1. So this is quite a complex mathematical problem, which involves using the Arrhenius equation twice, dividing it out, simplifying. Again, you could skip right to the simplified equation because it is given in Alex, and then plugging in what we know, and there's one variable, K2, and then working through our way through and solving for this variable. As you can see, it takes quite a lot of algebra to be able to do this, so it's very important that you practice with the algebra to make sure that you can solve these types of equations.